Emma Stewart and Kevin Schneider. Dr. Stewart is an Associate Program Leader for the Defense Infrastructure Program at Lawrence Livermore National Laboratory, and Dr. Kevin Schneider is a Principal Research Engineer at Pacific Northwest National Laboratory. They have both done this tag team for us a couple times now, so we're excited to have them. They're pretty enthusiastic. If Emma and Kevin are comfortable with showing your webcams, we do prefer that. So we'll give you a second to do that. Thank you, Dr. Stewart.
Can you hear me okay?
Yep, and we have just under 90 minutes for this. I'll keep you on time, and we'll say some questions throughout. But yep, we can hear you great. Thank you.
Hi there. Sorry, my office is set up sideways, so you're going to see one half of my face for this. I'm doing the quick introduction just now to Distribution Systems 101. The beginning of this is basically us telling you what the components are, what the building blocks are of the distribution system, what things look like, and what a guideline to everything you'll be hearing for the rest of the day, so that when there's words about what the system is, you can understand and associate it with a piece of equipment or a process or a type of technology. You're controlling the slides, correct? Or am I? Okay, got it.
Yeah.
So we've got this in 4 parts here. I'm just quickly introducing before we move on to Kevin, who's going to talk about system fundamentals. So what the basics are of how electricity and power flow actually works. What the power system looks like in the distribution equipment, knowing which components are what. I'm then going to talk a little bit about communications and sensors, which is basically what we can see and how do we actually see it. And lastly, this is a slightly new module that we've added, which was looking at industrial control system cybersecurity, a very brief introduction to what we actually look at and how it relates to the communications and sensing system and to the distribution system. So our goal is basically, this is just setting the foundation for the rest of the day for everyone, knowing the basics and the terms and the present state of our distribution system. To be clear, it is very basic. It's not set up for people that know a ton about the distribution system. And the ways we've done this prior, there's a massive varied set of knowledge in the room, from very basic of how does the switch work up to the actual knowledge and detail of what we're talking about. So yeah, so we'll move on to Kevin and the first part of power systems fundamentals.
Okay, next slide, please. I apologize, I don't have a webcam set up because it's not enabled on my computer. So going back to a comment that Paul made, is when he was talking about the architecture work, a lot of that was looking at, you don't want to select the windows before you start building your house. This presentation is really going to roll this all the way back to what is a 2x4, what is a board, what is a screw, et cetera, et cetera. So when we start looking at the power system fundamentals, and I'll really break this into 2 areas, which is the fundamentals of electricity itself, and then looking at some of the characteristics of what we see as the modern electric power system today. Next slide, please. What you'll see is I like to have a lot of pictures and figures on these. So when we start looking at the fundamentals of electricity, I'm not actually going to start with the 18th century here, but I will start with some pretty basic level material. So next slide, please. And starting with the pictures of Tesla and Edison, looking at what are the differences between alternating current and direct current. The reason this is important is, one, it is a fundamental difference between it, but we're also starting to see more of a convergence of these in power systems than we have in the past. So in a direct current, you could think of this almost like a battery. You see a voltage supply that's relatively constant over time. There might be some variation, there might be some ripple, but the key is that if you were to put a meter on it, you would see X volts and it would more or less stay the same. This was what the early power systems were, and this is also what we see being produced by batteries, solar PV, electric vehicles because of their batteries. And so we're seeing more and more of the direct current. But the early direct current systems really didn't become widely adopted. The reason being is at the time it was difficult to change the voltage levels. And so this is where alternating current and the Tesla side came in, is because if you look at the waveform of an alternating current on the right there, you see that it starts at 0, it goes up to some peak level, back through 0, goes to a minimum level and comes back to 0, and it does this in the US at 60 times a second. The benefit of this is it allows you to use equipment such as transformers to effectively change voltage levels. This is important because if you're going to move power at a distance, it's more efficient to do it at a high voltage. And so that's really how we ended up with the alternating current system. Is since we had our generating stations, in some cases further away from our cities, the alternating current allowed us to raise the voltage and move power long distances more efficiently, which we couldn't do with direct current. Now today with power electronics and inverters, that's being revisited, but there really becomes the question of how are we going to start to interface the AC and DC systems. The last thing I'll say is that most generators at big central plants, they produce alternating current. Smaller PVs and even some of the larger PVs will do direct current, and you have to either interconnect those systems either through power electronics or some type of rotating converter. Next slide, please. So alternating current, the way that they're traditionally produced is you basically take a magnet or a coil, you put it on a prime mover, which is just a fancy way of saying a rotating shaft that's being driven by water, steam, combustion, some type of motive force. And this is what we call the rotor. We rotate this around at speed, and when you put coils around it, a voltage is induced in those. And that's kind of what we're seeing here on the right. And you end up with a single, what we call a phase, of a voltage that becomes a sinusoidal form. And that's how we traditionally produce alternating current. That's what the vast majority of power in the US is generated as natively as an alternating current. The reason it alternates is because you think of a bar magnet, there's a north and a south, and as you spin it in a circle, sometimes it passes the north face, sometimes it's the south face, and that's how we go positive and negative in those cycles. With some of the more newer technologies, you can also produce an alternating current with solid state inverters or inverters, power electronics, a number of different names, but the process is fundamentally different. I'm not going to get into it too far here. It's technically pretty close to the same. There is an equivalency. So one thing though is that when we produce power, we don't do what's called a single phase because it'll have oversized generation, it's inefficient, it's not cost effective. And so what we'll see generators in the US is that we have a polyphase system, specifically 3 phases. The polyphase system was the basis of Nikola Tesla's patents and his concept, but in the US this has really manifested itself as a 3-phase system. And what you'll see here is another simplified diagram where you have the rotor spinning in the middle and kind of a mess there. And then you'd have 3 sets of coils. And what you'll end up with are 3 independent currents that are being driven by the voltages. Now, an interesting aspect of those is those currents, because you still have a single magnet in the middle, or electromagnet, what you'll see is the phases of those voltage waveforms are out of phase, meaning that the north face of the bar magnet in the middle can only be aligned with phase A, B, or C at one time. So with 360 degrees in a circle, what you'll find is that these phases are these voltages and currents are 120 degrees out of phase. This is important because what it means is that if you look at the power system we have today, we typically use 3 power carrying wires, and they each have their own, each is considered a phase with a voltage waveform, current flowing, and they are out of phase with one another. And the system has been designed to accommodate that. Next slide, please. And this is a picture of what that looks like when you overlap them, where you have voltage A, B, and C, and then you'll have a current that those voltages drive. So if you were to look at the power lines going over the hills or down the streets at any point in time, if you were to pick it, you could see that 1 voltage would be very high, 2 might be negative, 1 might be 0, and so they vary at time. Next slide, please. So this is when you have 3 different phases, the question is, how do you connect the loads to them? And this is how you would connect very large loads. And when you have 3 different phase conductors, there's different ways you connect them. Either what's called phase to ground, which is what we have on the left side, the Y or star connected, where that little central point becomes something that's connected to electrical ground, or on the right side, what we call delta connected, where things are connected phase to phase. For most of the loads in the system, we use what's called the left-hand side, the Y connected, because that allows us to give a grounded system. So I'll talk about this a little bit more, but in general, at the bulk transmission system, kind of the super highways of the power system, we use these delta connected systems on the right, but when we go to houses and loads at the lower voltage levels, we tend to use a 4-wire system on the left. the left is showing 3 wires, but it's not showing the 4th wire as the ground. The point being is that there's complexity in how you connect these different systems. Next slide, please. Next slide. There we go. So one thing, I'm not going to start going into equations here, but what I want to highlight is there are different types of power that you'll hear utilities talk about. And the reason for this is when you rotate these electromagnets around a coil, you will get a sinusoidal change in voltage. If a system has purely resistive loads, you'll also have a change in current that is in phase with that voltage. But because of the physical nature of the system, we have inductance and capacitance. This causes a slight phase shift in the current, and you'll see that in the low or the upper right-hand corner, where what you'll have is when the voltage is at the peak, the current hasn't quite reached its peak. And then as it goes back down, at some point the voltage is at 0, but current is still flowing. And depending on whether that phase shifts to the left or right, you have what's called the power factor of the system. And what this does is it results in different types of power. So active power, this is power that's used to consume work in the physical sense. This will light a light bulb, produce heat, move an elevator up and down. This is the active or real power that we want and we can make use of. But we also have what's called the reactive power. This is power that is consumed to maintain the electric magnetic fields, and it's represented by the component of the voltage and current that are out of phase. So the fact that voltage and current aren't lined up at some point means there's a little bit of power in there. And unless we have a purely resistive system, we start to have reactive power. And mathematically, this all shakes out. And then at the end, you have what's called apparent power, and this relates the active power and reactive power. This is important, if we go to the next slide, because the apparent power will drive how much power or current is actually flowing down the line. And so we have what's called the power triangle. And so the active power, or P, is along the x-axis here. Reactive power is orthogonal at 90 degrees. And then the apparent power is S. This is where why reactive power matters, is because you can see that because apparent power is the hypotenuse, if you want to deliver a certain amount of active power to do something, the more reactive power requirements you have, it will increase the value of the apparent power. And through these equations down here, that means it requires more current. And so the big takeaway there is that if you have too much reactive power requirement in your system, it requires more current down the lines, which means bigger voltage drops, more current or more conductors needed, and it makes for a more complicated system. And so this is where you'll see utilities talking a lot about reactive power compensation. They'll deploy devices such as capacitors, and this becomes a fundamental issue of operating electric power systems, is managing your different types of power. How do you balance the active power you want to deliver to customers with the reactive needs of both the power lines, the transformers, and the load? And how do you do that to make the system as efficient as possible? The most efficient system would be if there was no reactive power and you could deliver it purely as active power. Next slide, please. So that's the mechanics of how electricity functions. But the next thing I want to do is look at what are the characteristics of the system. So we know that we use a 3-phase alternating current system, but what else are the other key defining characteristics? Next slide, please. When we look at the bulk transmission system, as I mentioned before, we use a 3-wire balance system. So when you're looking at the big metal towers that go across the long distances, you'll only see 3 power carrying wires on it. The frequency is at 60 hertz nominal. There are small variations, but over time they average to 60 hertz. The voltages for this are anywhere from 69 kV up to 765,000 volts at the alternating current level. 765 really only exists up in the Northeast. 115, 230, and 500 are the most common for most of the country. This is where you're moving power for hundreds, even thousands of miles in some cases. And primarily, this is all overhead conductor. You can put some of this underground, but putting high voltage transmission lines underground can be very expensive and challenging. The transmission system is primarily supplied by central generation. This is on the order of hundreds and thousands of megawatts. So you start to get in the gigawatt range. Even when you have renewables connected at the transmission level, you're talking about multiple 100 megawatt solar and wind farms. This system is operated as a network, meaning that it is a mesh system with multiple paths in the system. And this is very important for both reliability and resilience, because if you lose any one element, it shouldn't cause a loss in load. This is referred to as an N-1 criteria. The majority of generation in the country is tied at the transmission level. We're starting to see more going at the distribution level, but currently it's primarily at transmission. The operational characteristics is this tends to be federally regulated, because you start to talk about interstate commerce. Now there are some notable exceptions: Alaska, Hawaii, parts of Texas, but for the most part, NERC and FERC, or North American Electric Reliability Council, through the Federal Energy Regulatory Commission, has some overview of this. There's mixed ownership models where you have some private companies. Examples include American Electric Power, Puget Sound Energy here in the Northwest, but you also have federal organizations such as the Bonneville Power Administration and the Tennessee Valley Authority. While there are effectively 3 interconnected power systems in North America, they are in effect one large electrical machine with over 100 interconnected operational entities called balancing authorities that manage it. So this becomes a very complicated system because of the different, not just the technical aspects, but also how we organizationally divvy it up as a society. Next slide, please. If you think of the bulk transmission system as the superhighways, the distribution systems become more of the rural roads. This is where once you move the bulk power into a region, you step it down for use. So I live in Seattle, so we have a number of 230 kV key feeds that come into the city, and then it gets stepped down into the distribution level from there. These are typically 4-wire unbalanced systems. What I mean by 4 wires, we still have 3 power conductors, but we also have a grounded neutral. The reason for this is it allows us to have single and double phase laterals. The reason for this is we don't have, unlike Europe, we don't have 3-phase power going to our houses. We do have 3-wire power, but it's fundamentally different. We're capping power off a single phase conductor, and that's what powers up your house. The benefit of these single and double phase laterals is it allows you to serve lightly loaded areas. That way you don't have to run 3 power conductors everywhere. It's more effective and cost effective. Still operates at 60 hertz, which is driven primarily by the transmission system, but the voltages are typically below 50,000 volts, with 1247 being the most common. At this level, you're generally looking at the sub 100 megawatt levels and typically less than 20 miles distance. Once again, you're a lower voltage, so you don't want to move power as far there. At the distribution level, because the voltages are a little bit lower, you have a combination of overhead and underground lines, and these are supplied by the transmission and sub-transmission systems. While the transmission system is typically operated in a radial nature, a network nature, distribution systems, for reasons of cost, are generally operated radially. If you get into an urban and suburban area, you can interconnect things, you can switch around, but sometimes there are no adjacent circuits to feed from, so you may have a single circuit that goes out into a rural area, and if there's any break along that circuit at any time, all the customers lose power. Generation-wise, historically there's been minimal generation, but that is starting to increase because we're seeing more solar PV. Operationally, these are regulated utilities, but they are far more complicated. There's different ownership models. You can have investor-owned, municipal utilities, rural cooperatives are very common. Up here in Washington State and Oregon, we have public utility districts. And so, once again, this is still part of the same interconnected system. You know, the transmission system, you have 3 different interconnected grids, but they all feed the various distribution systems underneath it. Electrically, it's all one big system, but organizationally, it's much more split up. And so we have somewhere on the order of a few thousand distribution companies being served from the various transmission companies. Next slide, please. Carrie, should I stop for questions at this point?
Yep, we're just going to pause for questions. I'm not seeing any come through the chat box, so I believe we're pulling up the second set of slides here for you. Just for the audience to know, this is the part of the training where the engineers feel great that they can sign off and that they know everything already, and that you'll see soon that that's not necessarily true. The lawyers, the attorneys start to think that this is outside of their realm, and you will also see soon that it is not. So just wanted to address that really quickly. This is that part where of the training that gets we start to get some people thinking about some stuff. So Kevin, are you up next, or is it Emma?
I am part two. It's still me.
All right. I guess you're going to go straight into it.
Correct.
Thanks, everyone.
So I just gave an overview of kind of some of the big operational concepts, but the next part is to go into looking at the specific key pieces of equipment that are out there and why they're relevant. Next slide, please. And to do that, I want to look at kind of the two elements of the substation equipment and distribution equipment. This is really focusing at the 50 kV or 50,000 volts and below level. I'm kind of passing over the transmission level stuff here. Next slide, please. When you look at the substations, they are perhaps one of the most important pieces of the power system. The reason being is they are next to the large generating facilities, they are the next largest location for capital assets. This is where we have some of the largest and most expensive piece of equipment, and the piece of equipment that, if they fail, have the largest impact in the system. Next slide, please. And so when you look at distribution systems, their role is, how do I phrase this? There are multiple substations when you go between the source of generating power and consuming it. The reason goes back to what I said before is we typically generate power at a distant location and we want to get it to the house. For that to be efficient, we want to move it up to a very high voltage in the hundreds of thousands of volts, but we need to get it down to lower voltages in the house. And so, or the building. And so the substations are where that occurs. For the distribution level, the main purpose is to step down the voltage from the transmission levels, which can, for this is typically 115 to 230,000 volts, down to the local distribution levels. These are commonly anywhere from 4.2 to 34.5 thousand volts on the secondary side, which 12.47 being the most common. And that would probably be about 90% of the circuits in the US, but there are still a number of legacy lower 4.2 kV voltages, and then some utilities have used 13.2, 13.8, 24.9. This really becomes a trade-off. The higher the voltage, the lower the losses, the more efficient it is, but also the more expensive equipment can be. The reason being you need larger distances for clearances, more insulation, things of that nature. And so what you'll find is that this will vary from utility to utility based on what their needs are. Next slide, please. So within the substation, the most expensive piece of equipment is the substation transformer. And these are examples of just some that I've come across over time. These are the key piece of equipment because all of the power that gets to the distribution system, and therefore the end use loads, has to go through this equipment. These are large pieces of capital equipment that are expected to last 30 plus years. And in some cases, they'll be in operation for over 50 years. One of the biggest contributors to the degradation and failure of these pieces of equipment is overloading the unit. And we'll talk about this more as we go into it later, but from a planning perspective, this isn't as easy as it sounds, because if you're talking about a piece of equipment that could be in operation for 50 years, when you first put it into operation, how much load should you put it under? Because we know the system will change over time. And so what you'll often see is that transformers, when they first go in, may be lightly loaded, but over time, due to load growth and various changes, they may experience various overloads at different points in their time, and that will affect their lifetime of the equipment. And so this is where there's a lot of work that goes on in the planning arena. What's the proper level of loading, asset management, and this ties into a lot of other central issues in power system operations. Next slide, please. Once you get outside there are a number of pieces of equipment, other pieces of equipment within the substation, but really the transformer is the key one. That gets it down to a voltage that is high enough to move around a moderate distance, 10 to 20 miles, but not enough for consumption. So we have to move the power throughout this local region, and it requires a fair amount of equipment to do that. Next slide, please. When you start to look at the key piece of equipment, what you have are the conductors for moving the power around, transformers, because we're going to have to move the voltage or change the voltage a little bit more still. Voltage control devices, maintaining the voltage within the acceptable ranges are important for lifetime of equipment, but also for not damaging customer equipment. You have to have protective devices and then various switches to reconfigure the system as well. Next slide, please. The first of these are overhead lines. These are just some examples of different forms they can take. Unfortunately, I actually picked all three-phase lines here. I didn't pick any single or double-phase laterals, but I'm sure people have either seen them or maybe you can go look for them next time you're driving around. Sometimes you'll only see one overhead line and then one neutral conductor, which is kind of hiding down lower. But overhead lines are much more common than the underground lines, primarily due to cost. These are typically made of aluminum and steel. Sometimes you'll see copper, but copper tends to be a lot more expensive. For the most part, these are bare conductor wires, meaning that there is no insulation on the overhead lines. So if anything comes in contact with it, you will now have contact with up to 34.5 thousand volts to ground, that's how we get faults on the system. When they do come into contact, that's a fault. And the most common things to cause this are vegetation, animals, and in some cases, people. In some cases, utilities will put a light sheathing on them if there's a lot of light vegetation. It's not meant to offset continuous contact, but it can help a little bit, but that adds weight and cost. Next slide, please. In some applications, people want underground lines. Sometimes they're direct bury, sometimes they're in conduit or in vaults, as you'll see on the upper right there. And these are used in locations where maybe you have a lot of momentary faults, you have very windy areas, sometimes in urban areas where overhead lines aren't practical. In fact, that upper right is a part of an urban core where you can't necessarily run utility lines down the street. And then sometimes communities just don't like the visible or the visuals overhead lines, and they want to have them undergrounded. Problem with that is it's anywhere from 5 to 10 and sometimes more times more expensive. And so that can be a challenge. Additionally, if you have direct bury lines, faults may not happen as often, but if there is a fault, locating it can be a lot more difficult because you may not see the fault because it's buried underground. And so restoration times can be significantly longer, that's a consideration for customers. Next slide, please. Once you're able to move the power line around the system, the next one is how do we get power to the actual customers? That's you and I at our houses. Sometimes you will have what are called primary customers. These could be large industrial or commercial customers that would bring primary voltages in 4.2 to 34.5 into the house or into the building. But for most of them, you'll have a secondary customer. And these upper right-hand pictures are examples of what your house will be served by. These transformers are called secondary service transformers. They routinely last 50 plus years, sometimes longer. And this is how we convert from a single phase of the three-phase system to the three-wire system in the house. So for people who've done any wiring in your house, you do have a white, a black, and a ground. What we use in the house, the difference is that is 3 wires, but they're not all power carrying. And for folks who are familiar with circuit diagrams, on the lower right, there's an example where you connect a single phase of the transformer from the power conductor to ground. And then on the lower hand side, you would have the wiring that you'd be used to in the house. And in the household, you would pull off from X1 or X2, and that way you'd have a hot, a neutral, and a ground. These transformers, there are millions of them throughout the country. While they are transformers like they are in the substation, they don't have the same capital cost. They're more of a commodity element. Next slide, please. Key thing is that will get you voltage to the house, but one of the key things is you have to maintain voltage within a set line. Within the US, we tend to use ANSI C84.1 range A. And the key here is that this diagram here shows the voltage from left to right of the left, assuming to be the substation, and the right is an idealized line as you go out. And because of the different loads on the system, what you see is the voltage starts to drop. Now, another key aspect is what we'll see here is that as the load on the system changes, the voltage can vary as well. And so at nighttime, there's not much load in the system, so it may be kind of a higher load at the end of, or higher voltage at the end of the circuit. But as you load it up, it'll start to drop down and you can get a lower voltage. Next slide, please. And so one of the things that we'll do is sometimes there'll be too much voltage drop on the system, and so voltage regulators will be installed on the system. And so the lower right-hand example shows a case where the voltage starts to drop down, and without a voltage regulator, it would have gone below that 114 volt limit. And so the voltage regulator taps the voltage back up. These are typically installed sometimes at the substation, sometimes on the distribution circuit. Sometimes you can have multiple banks of them because you have so much of a voltage drop if it's a very long circuit. These can be installed in banks of 3 of them, as we see in the picture in the upper right, or sometimes you'll see individual ones on laterals. These are electromechanical devices, and so while they can't control the voltage, there actual are mechanical contacts in there with motors and contactors. Every time it operates, there is a bit of arcing, and so while you can install these to address voltage issues, over time, this becomes something that requires maintenance, and so there's not only a capital cost associated with it, but there becomes an O&M cost as you put more of these on there. Next slide, please. I mentioned before that you also have situations where we have non-resistive loads in the system. In general, the system tends to act like an inductor, a set of coils. The reason being is not only do we have long lines that we push the power down, but we also have motors, which are coils. And so one solution to address this is that we can install shunt capacitors on the system. These are another way to address the voltage drop on the system. Now, they can only do this to a limited degree. They're not as effective as voltage regulators. All they can do is offset the reactive power consumption of motors and loads. And so what you'll see on the system is that these can be installed either as directly wired or fused in, or sometimes they'll be switched values or switched banks where you can switch them in at different times based on the voltages. One of the key things, though, is that if you start to deploy these along with voltage regulators, you're now putting multiple control systems on a single circuit, and you have to coordinate their operations so they don't start to fight against each other. This is some basic control theory that historically has been relatively straightforward with utilities. They have good practices for how to do that. But as we'll see in some of the later presentations, this starts to get more complicated as you add things such as solar, electric vehicles, and other elements on the system. Next slide, please. So once you're able to regulate the voltage on the system, you need to consider what happens when the system doesn't operate as you intend. Specifically, what happens when a fault occurs. Because of windstorms, ice, animals, vegetation, drunk drivers, any number of reasons, we are going to have faults on electric power systems. And so we have protective devices that are designed to interrupt the flow of fault current to protect the equipment. Because of the voltages involved here, protection systems will not save a human's life if they touch a power line. If they touch a primary voltage, there is, in all likelihood, they will die. These are designed to interrupt the flow of current, to protect the equipment, and to make sure you don't have live lines on the ground for very long. Now, there are different types of these. The first one is a circuit breaker. There's a picture of that in the upper right-hand corner. This is actually a gas-insulated breaker, and they're typically located at the substation. They're used to protect the transformer or an entire circuit. When a fault occurs, they open. They can also be remotely operated to open as well. Perhaps one of the more interesting devices is called the recloser. It's similar to a breaker, but it has the ability to open and close more than once. And so the key is that we know that some faults are momentary. What I mean by that is there's a difference between an electrical fault when a power line is laying on the ground and when a crow is pecking on an insulator and electrocutes itself. The latter is a momentary fault that's only there for a minute and then clears. And so the idea of a recloser is that it is closed during normal operation. If it sees a fault, it opens up, but it will automatically reclose back in afterwards to see if the fault is still there. These are generally operated in a 3 to 5, what we call a shot scenario. It'll operate 3 or 5 times. If it still sees the fault after that, it'll lock out. These are very important for reliability because if you don't want to have a situation where a utility has to roll a truck crew out every time a bird lands on a power line. I should say every time they land on a power line bridging the insulator. Birds can sit on the line just fine. And so by putting these on the system, it actually takes what would be a permanent fault and turns it into a momentary fault, which is much more efficient for resilience and reliability. Reclosers are rather expensive. Newer ones are vacuum bottles, so they're smaller. There's microprocessor-based equipment in there. It's not cost effective to put those on every load in the system. So what you'll see in more common use are fuses, where a fuse will be tied to every secondary service transformer on your system. Fuses are just like what you may have seen in older houses or automobiles. It's just a fusible link that when too much current is pushed through it, it opens. There's no way to reclose it. A truck crew has to go out there and replace it. And so these are the fundamental elements of protective devices on the system. Next slide, please. Slightly in contrast to protective devices, I should say, while a protective device can reconfigure the system by opening and closing, switches can also do the same function, but they are not designed to interrupt fault current. And so their primary function is to provide electrical isolation. And so this could be either for maintenance, where the crew will go in and open up to work on a transformer or a piece of line. They could manually switch different sections of conductor to other circuits, but they are not productive devices. If a fault occurs, they will continue to allow fault current to go through there. When you have these at a substation, they can be used for manually reconfiguring the location of which circuits are powered by which transformer. Various pieces of equipment can be isolated. They're really used for maintenance. At the distribution level, once you get out into the circuit, they can be used for manual reconfiguration of a circuit or feeder. The problem is that requires a truck crew, and that can take a very long time to do, especially if you imagine during a large storm condition with a lot of trees being down, depending on where you live. It could take them hours to get to the location if the roads aren't cleared. They can be used, as I said, as part of a repair strategy, but they do have a much more significant lead time for operation. And then switches can also be remotely controlled, just as breakers can, through your supervisor control and data acquisition or SCADA system, although they generally tend not to be operated under load because, as I said, they're not designed to interrupt fault current. They're just simple kind of dumb knife switches like you'd see in a Frankenstein movie. And so operating those under load can cause damage to them. The advantage to them is they're cost effective. While a recloser will cost tens of thousands of dollars, and it can cost a lot to mount it on the system, these are far cheaper to purchase, less maintenance as well. And those are kind of some of the basic devices that we'll start to use for further conversations on the other. As I said, these are kind of the base elements of the nuts and bolts of the system. And now the other talks coming up, we'll talk about how do you plan the system using it, and then how do you operate the system using this equipment. And that's it for those two.
Hey, Kevin, great. Thank you so much. We have a couple quick questions. I have three. The first one is, what is a public utility district? I believe that's the service territory. Can you confirm? Kevin?
Sorry, I didn't quite get the question there.
No problem. The question is, what does public utility district mean? I think that's a service territory.
Yeah, so I mentioned as a public utility district is something that exists in Washington and Oregon, and they are just another form of a utility. They were formed because of the history of power in the Northwest, where independently owned utilities had supplied powers to some customers, but they hadn't done a very good job. And because they were already being served, rural cooperatives were not allowed to come in and form their own association. And so public utility districts were passed as a legislative act that allowed communities to band together, claim eminent domain, and form a public utility district to provide service to those customers.
Thanks. Next question is, what percentage of load is generally considered safe, or what we would recommend for safest use during distribution system transformer? Can you tell me something about auto transformers?
Yes, so safe load of a transformer is, that's a very large discussion. So steady state load, you want to keep it below 100% because the rated load is what it's designed to cover from an indefinite period of time. Transformers can take surge loads that are higher than that, but the degradation in lifetime goes with a fourth power of overloading because of thermal effects. So while you can overload them, that will impact their life. So the idea is that you want to keep them below 100% at all time if possible. But this gets into a very complicated asset management discussion of, since these are so expensive, you don't want to load them at 25% because that's a stranded asset. Now, an auto transformer, for most power transformers, you have two independent coils and there's no electrical connection between them. It all goes through a magnetic flux. That's very good for providing electrical isolation, but it requires a larger device. An auto transformer actually is a single coil wound around on itself. It allows itself to change voltage in a much smaller form factor, but it doesn't provide electrical isolation. This is actually what voltage regulators are out on the distribution circuit. They're variable tap auto transformers. So the trade-off is that they are a different type of transformer. They provide no electrical isolation, but they can be smaller. They can provide a smaller range of voltage change, and they're more cost-effective for some applications.
Okay, we're going to move on to Emma's next presentation, and then we'll see if there's any questions at the end.
Sounds good. I'll hand it back over to Emma.
Hi there. I'm quickly going to give a couple introductions to how we sense components on the grid and how we communicate them. So Kevin's done a great introduction to what all the pieces are that go together. I'm just giving the basic introduction as to how we actually measure them. So first slide. So very basically, what is actually sensing and measurement? What are we trying to do here? How do we get from the point of measurement to the point of useful information and action? We hear a lot about this whole thing of needing to give actionable information to the operators and the planners, but what that actually means and how we get to it is a varied pathway. But for every component, no matter if it's transmission, distribution, at some point we're measuring this system electrical response. So we're measuring the behavior of the electrons on the system or the behavior of some other type of component. That passes up to the point of connection to the power system, the measurement device, communications or local analytics. In some cases, we communicate the raw data up. In other cases, we keep it local and look at what's going on locally. Then that translates into something useful that somebody in the planning or operations department can do. And then there's an action that they can take from that information. So just as a basic introduction to when I say sensing and measurement, what I'm actually talking about here. So this is sort of also talks back into things that we heard from Joe at the beginning about things like system forecasts, changing natures of loads. These all start with some basic measurement of a parameter, be it irradiance or type of or solar irradiance on the system, or just the voltage and current that's happening on the system as well. So next slide. So communications can be supporting all different things on the system, from real-time operations to just planning. I expanded this discussion from its original version a little bit here to focus a little more on the communications of the system. So it gets talked about a lot out there of what are we communicating, how do we communicate, how good are those networks, and what does it actually mean? So once we actually measure it, how do we get it to the right people or to the right systems, and what do they do with that information? So here, like telecommunications essentially supports all different layers of our system. Everything from real-time monitoring control, the protective relays communicating their status, energy management, outage management, the communications from smart meters, which I'll talk about in a little more detail, and substation automation functions. A lot of the systems Kevin spoke about as well have these electromechanical functions that respond directly to an indication on the system. For example, protection will trip without the need for any kind of communication with the rest of the system. Part of that's to do with things like latency, and also safety is paramount. So losing the system is more important than somebody being hurt, for example. When we start with sort of advanced applications in here, the utilities can rely on both public and private communications networks. So something as a good example here that I have, we're trying to install a new sensor type with PG&E at the moment at a remote substation that's a pretty nice location. It's down by the beach. But there's basically no communications to that substation that we can use for this type of sensor. So to enable us to measure this advanced acoustic sensing here, the utility is going to pull a circuit from AT&T to use to get the data back actually to the lab in this particular case, so that we can analyze this new data stream. So there are fiber lines at a number of utilities. Some are more advanced than others, and it changes drastically based on rural versus inner city type networks. So there's no one model that's really applied in a blueprint way across the system. Next. For whatever reason, half my slide is not on the screen here. Oh wait, there it goes. Huh. Okay, I think there's just a slight latency, funnily enough, when we're talking about communications between what I see and what's on the screen.
There's animations.
Okay, so there's different communications that we can use throughout the grid. Like I said, it's different depending on whether we're up at the large generation systems and what's used there for transmitting control and monitoring messages within plants. So I'm talking about like plant information here, where you would see the status of a machine or the status of the large generator reporting up to either internal measurement or out to the independent system operator, for example. Various things are used here, which you'd be surprised in some cases just the plain old telephone service is still used. But fiber optic is becoming much more common, and in remote areas, cellular communication also. When we start to talk about the transmission system, there's power line carrier systems where basically we can use the power lines to transmit certain amounts of information. There's various limitations on using that and problems, but it's used pretty commonly. Substations themselves can use various degrees of radio and wireless within them and between substations. And then also we do have down to the mobile radios and satellite phones, which the field crew themselves might be using during restoration and repair, depending on where they are. Also in some kind of emergency conditions, they do have radio systems that people like the National Guard would bring in to form a new network behind the system. And distribution system, which is the primary focus of everything we're really talking today. Some of the more I don't know if the word is advanced, but some of the more exciting things that have been going on recently are to do with utilities who have fiber optics installed to basically every component. It's really interesting to work on controls with those kinds of systems because you don't need to worry quite as much about the latency between devices, for example, which can be the latency can be a primary limiter for some of the controls we want to look at. Also, there's things that, again, mobile radio, satellite phones used for field crew. And then we get down to the smart grid communications, which is primarily looking at the smart meter networks, how we're controlling the distributed generators, and also there's a degree of wireless mesh networks. Pretty varied from the very high levels down to the customer level. In general, there's a bit of a gap between the distribution substation and the customer smart grid communications. We don't tend to have very much communication built in already between those 2 points. So that goes back to my story of installing a new sensor. When we're missing the substation has its supervisory control and data acquisition system, the customer has their smart meter system. What do we actually do in the middle, and what does that look like at the moment is one of the focuses of a lot of our work. So next slide. So one other thing, and I think there's an animation or a click here as well. One of the things we look at here are the interdependencies in the smart grid communications. It might complicate certain new functions that will be talked about, I believe, in the next session with Kevin and Barry. Also, where we're talking about distribution automation and the devices that are used there. Some of these interdependencies are great and extremely useful, and some can cause issues with what happens when we have an outage. So just as a one singular use case of where communication is both limiting and useful here would be in the distribution automation, where imagine we have a system where we need to communicate between components to detect and isolate faults and for remote operation by the operators themselves. If we start to lose power to the communication systems themselves, in various cases, we can't send operational commands to those devices. Or if there's some kind of bandwidth limitation being caused by, say, every single smart meter reporting through the same system, which it shouldn't necessarily do, but in some cases they're using the same backhaul system. If we have those communication issues, we can't really talk to those devices. So deployment of communication strategies for smart grid sensing is something that really requires a degree of thought and planning into both the current state and also sort of future-proofing the system so that when you deploy advanced applications, you actually built in the capability to do that already. The next slide. So I show this every time, and it's really out of date, but when you go visit various distribution operations centers, there isn't really that much difference between what's there and what's now. We still have map rooms in distribution utilities as well, so visited a number that will pull out the maps to double check things. So the expectation may be that we can communicate with every single component in the system and have these great visualization tools. But in a number of cases, we still need to be able to work with sort of rural locations, which might still be operating with paper maps and operating just fine with paper maps. But as we bring in more advanced applications, we need to consider how do we digitalize a lot of these components as well. Next slide. So what do we actually want to measure and why? There are big questions for research and industry. There's been a lot of work into what the architecture of a sensing system should actually look like and getting the most valuable sets of information out of sensors that are being developed. So we need to actually, when we're talking about installing sort of new measurement devices, we really need to think about what are we actually trying to measure? Where do we need the measurement analytics to be? So are we looking at something that's needing to be analyzed at the device itself, or a distributed location, say at the substation, or up at the central point where we need larger computing? Who actually needs the information that they're looking at, and when do they need it? How fast do they need to get this information? So when we start talking about data, we're down in the data collection can be down in the much higher frequency type of systems where we're looking at synchrophasors, which can be 60 to 120 samples a second of voltage and current. Looking at dynamic system stability, again, down in the small time frames, high frequency switching devices and responses of those. And then things like up to the sort of 1 second wind solar output variations, and then up to demand response on minutes or hours. And then we start to get up into things that are useful information that is derived from those data sets, which would be day ahead scheduling, planning for transmission and distribution out to from 6 months to 10 years, and scheduling of renewables, for example. So translating these, when we say we want to measure something like 120 samples a second, it's not generally because we think the operator wants to actually see 120 samples a second. That has actually been tried in a number of locations, and it was overwhelming at best. The thing we want to do is to actually create this actionable information, which goes into the sort of high fidelity analytics of predicting faults, for example. The next slide. I'll just step through these pretty quickly. So again, similar graph as before, but here I'm actually talking about the events versus the type of measurement that you might be looking at, and also mapping over here the type monitoring capabilities for different types of systems. So here we're talking about the 15-minute advanced metering infrastructure data, which is coming from the smart meters that are installed on the customer houses. We have I'll also talk a little bit about SCADA data, supervisory control and data acquisition. And then we also have at some locations things like power quality measurements and synchrophasor time stamping. Power quality is an interesting one in here because most locations won't just have a power quality sensor sitting everywhere in their system. That's not a reasonable choice for a lot of locations, but they do deploy them when something is going wrong. Often when a customer calls in and says their lights are flickering or they're having problems with their inverter staying connected, for example, the utility will send out a power quality sensor to work out if they can see where that issue is coming from. So that's something that's generally deployed on an ad hoc basis, but some locations want to have that measurement at substations, for example. Distribution system issues are also, again, on different time scales. Like I said, things like reverse power flow voltage problems due to output variation in distributed generators, for example, or voltage problems just because of other issues. Protection coordination, harmonics and transients, all down in the sort of sub-cycle level. And that all builds up into sort of capacity and utility rate case type things where all these different issues can contribute to that higher level of time frame. So it's important to have that monitoring in place. Next slide. So when I talked through the first sort of flow chart in here, we had like I said, what are we sensing? How do we sense it? Then passing it through to how is it communicated and how do people visualize it? So supervisor control and data acquisition is one of the things that's almost ubiquitous in substations across the country. It's essentially a combination of components that comes together to show you what the system is doing at the substation level generally, or out to specific devices on the distribution system. At the sensing level, we're looking at just measuring physical quantities, which is usually current and voltage, but also they can you can adapt it to measure things like, I think Kevin mentioned some of this, looking at the number of tap changes or operations of specific devices. Then we pass this up through the telemetry system here to be able to get it into a data acquisition server, which might be a plant information or historian system, which is important for my next set of slides. And that can help manage all your data from the different field devices and attribute it to the right component that it came from, a right location. Again, then you have your historian, which takes your real-time data and passes that out to the passes that into a system where it can be stored longer term, so you can pull that out when you want to look at what happened on the system. Then there's a human-machine interface, so where do we actually see the data and what do they want to do with it? So this is where we show what's going on in the system and where it's happening. So next slide. Again, this is an older picture, but it's basically showing what an operator might see from the SCADA system, which is a set of substation components. The purple and orange components coming together are a transformer. So this is a bit about why we show you pictures of what a transformer actually looks like, and then a picture of what it looks like to an operator that's viewing this in a digital way. And then stepping down to the lower part of the system in the orange, where it's showing the SCADA measurements that are at each of the different substation or feeder locations, which are the distribution lines that go out to the rest of the system. Next slide. So the second piece that I've got to focus on, like I said, there's not, this whole starting piece of presentation is about what the present state of the system. There isn't generally a huge amount of sensing in between the substation and the customer, so I focused on these two areas at the moment. There has been a ton of work on how to deploy better sensing between those points, but for right now, this is the main focus and the most common infrastructure that you'll see. Everyone sort of has heard that smart meters were deployed across the country. I can't remember how many there is. I think it's in the 100 million range at this point. That's far too many, but the smart meters were deployed across the rest of the system in a way over the last, I think, 10 years, starting with the ARA projects where sensors were becoming a focus for improving grid reliability. Their initial purpose was actually for meter reading being automated. That was the very primary purpose that they came out for, was to give more visualization into customer behavior on shorter time intervals. And allow people to monitor their power usage in a more accurate way. And so this started with typical activity of passing back voltage and usage at 15-minute intervals to the utility. That gets reconciled for billing, as in the customers receive a different type of bill that shows them in more detail what they're doing. Also helps them give advice to the customers of what is their peak power use, what could they be doing to reduce that if they're wanting to. The meters tend to report back to their access point a number of times a day, for example, 3 times a day. They're not generally continuously streaming unless this is set up for a particular function to do that. So they will report as a chunk of data back to the utility a few times a day or even once a day. Again, this goes back to the communications network piece, and why I've added this into this whole discussion was some meters you can query a subset of the information. So say you want to get 1-second data from a set of locations where you're particularly worried about some kind of power quality or power measurement issue, or even the condition of the components, that you can call for those meters to push that data back to the system. But generally that's a fairly decent burden on the communication system, so there hasn't necessarily been a lot of work to have real-time sensing come from those smart meters. There's 2 types of system you might see out there. There's the automated meter reading system, which is one-way communication. It's still a more advanced sensor than the initial electromechanical electromechanical meters we had previously. I don't think you can see it behind me. I actually have a mechanical meter sitting behind Iron Man back there that had taken from one of the utilities we're working with when they were getting rid of them all, because I thought it was pretty cool that they still had the sort of spinning dial in them. Then there's advanced metering infrastructure, which is what we're talking about here more clearly, which is two-way communication with sensors, and being able to get that advanced data back into the system and actually take action on it. The more advanced version of these also have disconnectability. They have various controls that can be put in place, but that's not necessarily used in a lot of locations. I do believe there was one use case which PNNL worked on, which was being able to automate reconnection of customers after a large outage in the Pacific Northwest. And that's some of the more advanced things that could be done with these as well. Next slide. So very basically, how does the utility see what's going on with their smart meters? One of the things here that you might notice is the outage management system. This is very high level for you to look at, but the white lines are essentially your distribution lines. And then there's little indications of where there's metering on the system. One of the things a utility can do with this is basically see where there might be an outage. Very basically, when smart meters are going down on the system, they basically change color on the system and show that a cluster of people might not have power. That might indicate to them that a certain transformer has blown or other things have happened on the system for that particular subset. The next slide. So one of the more advanced utilities that did a lot of work with their smart metering operations and customers was Florida Power and Light, partially through, I believe, DOE funding with Joe and a number of other activities to basically start to put state-of-the-art mobile applications to their smart grid, to their field workers out there. So this means things like being able to view what's happening on an iPad or a mobile device in front of them, rather than pulling up again paper maps or a large laptop and communication back to the central point. So this essentially was a system they put together which has a direct connection to the smart metering system and can see real-time outage activity, help with restoration confirmation of fault location. One of the really interesting things that was one of the applications a while ago that came out of this was being able to see the voltage data from the smart meters, enabled them to see that there was a set of components that had erroneous voltage data, which was all co-located with a certain type of transformer from a manufacturer. And it turned out that those all had a particular issue that was meaning they needed to be replaced or repaired in the near term. So giving some basic visualization can take us pretty far, but being able to integrate it is still an ongoing issue that everyone is working on as well. So, next slide. So just some further reading for this. In each of these slide decks, I've put in some other links that people can go look at and see what if they want to read more about the more advanced things that are going on to try and improve these. So some of that's just the grid architecture work from PNNL. One of my projects on data analytics. I believe there's a report here also on what integrating sensing data to modeling tools looks like. So that's the sensing set. Is there any questions here?
Hey, yep, just one quick one about smart meters. The question reads, can smart meters identify the locations of faults on the distribution system and report them automatically and quickly to the utility? And then does that mean that smart meters perform two-way communication?
The answer to everything is always it depends. It depends on what type of fault it is. It depends on the issue that's happening. There are ways, again, it depends also on the layer of analytics that you put on top of all this. I think a lot of the times when we answer questions on smart meters, we'll say it depends. If they're reporting fast and if they're reporting set types of information, yes, they're super useful for finding particular locations. Not necessarily for diagnosing exactly what faulted, but they're fairly good at diagnosing something has faulted, if that makes sense. There's a lot of work going on in this sort of analytics space of how to use high fidelity data with the smart meter data together to determine what has actually happened. But at the moment, fault location is generally the best thing that comes out of those, is at least knowing which phase it is and within which area can come from this data.
Thank you, and thank you for the questions that are coming in. We have about 23 minutes left in this session, so we'll just roll into your cyber presentation, Dr. Stewart, and then take some questions at the end. Thanks, everyone. coming up.
Okay, no worries. So I'll start talking if you like while the slides pop up. So the intention of this introduction to cybersecurity here, in my introduction, I'm a power systems engineer. I'm not a cyber person, but I've had to learn an awful lot about cyber in the last couple of years, just because it's becoming it's a highly publicized issue. It's something that is inherently now interlinked with everything we do in communication, sensing, measurement, and planning. So we have to be able to talk about what the impact of cybersecurity is on all the things we do in research. And so I think that's partly why we're integrating this to part of the training, was to help link together why it's important and why would you want to learn about what we do, best practices for cyber in the industrial control system. So next slide. So this may not be clear, but I know that people have probably read and seen about a number of the cyber attacks, and there's a couple of clicks to happen here as well. The Ukraine attack, everyone has heard about that, or assume everyone has heard about that, which was well publicized. But cyber attacks on our infrastructure are really no longer theoretical. It's happened a number of times over the last few years. We have some really good examples in here in the timeline of some of them are more serious than others. In particular, things like an attack on the airport, which was a teenager playing around with systems. The Bowman Dam, and I don't know if the clicks can go ahead, because that'll make more sense where I'm pointing to when they come up. Thank you. There's a really well publicized or a really interesting attack that happened in the Bowman Avenue Dam, which was in New York City, where we believe that was generally an attack that was meant to happen on a much larger system. But they targeted the wrong location. And also one that's the most interesting one recently that we talk about frequently is the Triton attack, where generally that was the first example of an adversary attacking a system that could have an impact that would be loss of human life. So attacks are becoming more serious. There's far more of them happening than are always talked about on the news. It's an interesting issue where we hear a lot about things to do with different names of attacks and shutdowns of things that are to do with malware. But in general, these are being tracked, and the impact of them is generally assessed. But it's becoming more frequent. It's becoming more serious as we move ahead, and as capabilities grow of different locations. Also, in the next slide, Dan Coates' public testimony about a year ago, talking about the capabilities and intents of Russia and China to map our infrastructure and what those issues might be. This is all public information, so translate that to how serious it becomes, that this has become a public issue to be discussed, that they're actively looking at mapping our infrastructure for nefarious reasons. So stepping through to, and I actually shouldn't have put the transitions on here, sorry, because that's making it much harder. Sorry about that. Next slide. So talking of the basics of what cybersecurity for the grid actually means was my first step here. I just spoken about communication systems. So within that, we have two types of network we talk about, the information technology network and the operational technology network. We can't deal with them on the same level for a cyber perspective. IT is generally a lot of the business systems and utilities and agencies. It's not the real-time sensing system. It's managing the data and the tools. For example, your own computer security is generally an IT system. Types of things that have been seen on the IT systems that are well publicized are ransomware attacks, where they lock out people's computers for a period of time. The IT generally manages the flow of data between different parties, whereas OT is the physical processes and machinery. The operational network, as it sounds, is the operational side, where we care more about the real-time systems, but latency is not generally an acceptable case. There can be redundant systems in the OT network, and again, the OT network is most of the focus of the work we do. Human safety is always the first thing that they care about in OT networks, then not disrupting processes and being tolerant to fault. basically here we're talking about safety, continuity, and fault tolerance for real systems. But yeah, when we talk about the industrial control system, we're generally talking about the OT network. So they have different requirements, different priorities, and different risks. And the conditions that you use for IT cybersecurity don't actually directly map into OT. There's essential processes for keeping your IT system safe, though, that can sometimes link into the OT side. So both need to be considered when we talk about the control system cybersecurity also. The next slide. So all of the work I'm referencing here comes from various sort of guidelines and best practices. The one I'm going to talk through in most detail is the National Institute, what does NIST stand for again? Sorry. the NIST Cybersecurity Framework, which gives us this approach that we take for most cybersecurity systems for ICS and how we actually talk about it in a way that makes sense to numerous different parties. It gives us the set of cybersecurity activities that are going on, and if you want to read more about it, I've included a link here. But I'm giving here a sort of brief overview of what this framework actually is and why it's important. The next slide. The cybersecurity framework is a set of conditions that help us to identify, protect, detect, respond, and recover from various types of cyber attack. It's colored this way. This is directly taken from the framework to help you understand what the different layers are that might be considered in this framework. What I'm going to do is actually basically talk through in basic terms what each of these 5 steps means, and then talk a little bit more about what the adversaries are and what that actually, what scale of response you actually need to those different types of system and what is being done. So next slide. So firstly, talking about identify, this is your planning step. Actually knowing and understanding what the risk is to the system, understanding how it works and how it's connected. You'll be surprised how often when we go talk to people about their OT security, we do a lot of work in mapping those types of systems. Basically, the understanding of what's connected to what can be generally fairly limited. IT is fairly well understood actually, but OT tends to be, well, we have this system, we have that one, we're not sure which piece is where. And so there's always a need to get an accurate inventory of the assets and the data and the people that are working on the system, and really understanding how that network behaves. So basically, when you're trying to defend yourself, you really need to know what you're defending against. So understanding the criticality of your assets also, and the level of protection you need for those, and having a comprehensive sort of risk management strategy for your supply chain, for example, and for your asset and business environment. The next slide. Protecting your system seems like the very first step, but again, identifying it actually is. Nothing in the system is actually perfect. There is no such thing as perfect security. We would love to say that you can defend against every single attack, but protection will at least make it harder for people to get into the system. So think of that as the fence and the gate guards to your system. Where they might want to manage the identities of people that are actually accessing the system, to be able to authenticate they are who they say they are, being able to segment systems in a way that keeps critical systems not touching non-critical systems, using encryption, for example. So basically everything here is about reducing the attack surface, which means reducing the number of points that someone can actually get into your system. Again, the objective is to just make it harder. So we do know that people will get into systems. We have accepted that this is the case. Nothing is perfect. But being able to even do things like patching your system. When someone tells you you need to patch your computer and restart it, and it's going to take 45 minutes, which happens to me frequently at the lab, it's important you do it. Like that's actually being able to protect your system. It comes down to basic things like being able to scan for those vulnerabilities and your firewall is actually configured properly. The next one. So detecting, so like I said, we've accepted publicly that adversaries will generally always find a way to get in, but once you actually know what is there, you can do something about it. So it's like an immune system or like taking antibiotics. Once you know what you have is actually key to fixing the problem and limiting its damage. So basically this is around being able to understand what your baseline activity is on the system, knowing what your network traffic looks like, having these libraries of known signatures and procedures for dealing with that, monitoring who's connecting to your system so you can detect quickly when someone actually is connecting that shouldn't be, and being able to report and investigate your instance. So important thing here is being able to have signatures and known conditions that can be reported to other locations. So if you have a particular incident happen, you can go through the cybersecurity center to respond and tell them what's happening. And that can be passed into the sort of intelligence community. It can allow them to get more information on what's happening and then enable things to be improved on other people's systems as well. This is kind of about the sort of teamwork between people as well. But timely detection of things happening through signature processes or anomaly detection can really give you a head start on being able to prevent the issue becoming more damaging. The next slide. So the response that you take is all about basically how we're mitigating. Again, I said information sharing through CISA, which is basically our sort of DHS, cybersecurity and infrastructure agency, which is considered the sort of nation's risk advisor for these kinds of things. But in planning for all of this, you need to have an instant response plan, like being able to execute that when something happens, you know how to respond to it, ensuring that like it cannot spread through the rest of your system and business as usual can actually continue. If you found something on the system, looking at forensic analysis on it and things like that, and having a playbook on how you respond through training and planning for the system. Some of this is also about mitigating newly identified vulnerabilities. So you don't, I'll talk about this in a few minutes, but we don't always know exactly what the vulnerability is. Vulnerability meaning a hole in your fence, or sort of the 0-day type things that are sitting there, someone finds them, they're able to get into your system through it. Understanding the scope of your compromise comes from at least understanding where the holes were as well. So again, having a plan, knowing how to respond to a cyber attack, communicating it properly, analyzing what's happened, and then performing improvements on the system so it doesn't just happen again are all keys to an adequate response plan for a cyber attack. So next. So lastly, how do we actually recover from these events happening? So as I said, the world is changing. As you know, we've talked about the DER in the system. We've talked about ways that we're automating responses and automating recovery using sort of different distribution system tools. But how do we actually recover from a wide-scale cyber attack is also something that is changing as we're getting more and more intelligent on what we're actually doing. So being able to restart a power system, the goal was always, imagine you've had this wide, end of days, wide cyber attack that's happened everywhere. If that happened in a physical way, we would not be quite as what's the word? We wouldn't need new plans for how it happens in a physical way. The operators and utilities know how to black start their system. They can step through a number of things, and the key there is always to safely reconnect all the components and then serve the load back to the customer. The recovery plan, when it comes down to there being a cyber event on the grid, needs to be slightly different. I think everyone who's done safety training knows they talk about pausing and thinking about what you're doing. That's exactly what happens or should happen now when we're looking at responses to cyber events, as in there needs to be a pause where the power side knows exactly what they're reconnecting, but they have to pause and think about how they recover the system, clean up the system, so get rid of all of what's infected it. Don't just reconnect and hope for the best, because you're probably just reinfecting everything that's there, or a lot of things. And then look at the safety aspects here of if you reconnect a system that's compromised or a spinning generator, there's more issues that can happen by doing that. So recovery from a cyber attack could actually be more time consuming, but it's really essential for continuity of business. So next. So just very quickly, some of the common paths, and this is from the U.S. Cybersecurity Defense in-depth strategies, where the common things that have happened included sort of devices that directly connect from internet to internet across ICS devices. You'll be surprised how many things like fridges can tweet have caused problems, or maybe you won't be. But people connecting things like their coffee makers that can talk into systems that were not designed to have outside tunnels into them is a problem. Things to do with remote access credentials stolen from authorized users, attacks on external facing interfaces where there's a link somehow through an external web server application or a historian that gets into the internal part of the system and then spreads from there. Insertion of infected mobile media. This is the USB stick thing that we hear about a lot. Don't plug in one that you don't have scanned. And then attacks through phishing emails. When you get those emails, we had a really funny one at the lab where they were trying to fool us all into joining Space Force. And those are phishing emails that you click on links and then it can pivot deeper into your ICS network from as the attacker finds their path through from the system. So just very basically, a lot of these are preventable by basic cyber hygiene and knowing thyself for the very first protect stage. But understanding the ways that they can pivot through into other parts of your system is also incredibly important. And the cyber teams are thinking through how to better map out what those links are and better protect against those. The next slide. So defense in depth, I've mentioned this fairly recently. It's a common term that's used and it is batted about as a buzzword or buzz set of words. It's a combination of all these approaches, making it harder to attack the system, enabling people to respond faster, isolating problems, and then recovering from this. There's a number of standards, controls, and countermeasures that are coming from all the people that work on the cyber side. Again, this also generally links through to the intelligence community, so you can look at the threats and vulnerabilities in the system and can translate that information in a way that utilities and people can use this to improve what they're actually doing, their operations, and their personnel. The next slide. So the last piece I have in here, we talked a little bit identify and protect in this strategy. What I didn't necessarily mention was the types of adversary that you might be facing in the system. The Defense Science Board has created the adversary tiers that are across the top of this, and this mapping is something that we've worked on at the lab of how we translate what we're doing into something that makes sense to the industry. For example, adversary tiers 1 and 2 here, we're talking about the kiddie coders, the people sitting in basements that manage to get into networks by finding known vulnerabilities that are there, and they manage to sort of zero-day attacks. The people like the kid that managed to take down the Massachusetts airport because he was hacking through something else, and so it's the kiddie coders that are worried about there. Adversary tiers 3 and 4 are the people that are a little more serious. They really are looking for the vulnerabilities. They're not just using ones that are known and publicized. And then we get up to the 5 and 6, or the people that don't need those vulnerabilities to be known. They can create them themselves. So when we talk through the different tiers here also, if you step on one, and the different technologies we can use to support that. Adversary tier 1 and 2 is something that is probably 90% of the issues fall into, which again is down these realms of protect, detect, respond, and recover. Again, things like basic cyber hygiene is your protection. Don't plug in USB sticks, for example. Antivirus systems and detecting what's going on, manual mitigation of threats and pre-planning. All these things, the reason they're in white, are well dealt with by sort of industry and basic cyber, following those sort of basic cyber rules. And industry is dealing with those, like the antivirus companies, the different types of technology that are coming from the commercial industry. When we get up to 3 and 4, that's where there's public-private partnerships are becoming more common and are needed to come up with advanced ways for us to defend against known vulnerabilities that are being exploited, or people that are using them in other ways. And so that's where we start to talk about advanced tools like encryption, data aggregation and threat detection, and also forensic analysis of the system. And so when we talk about these mid-tier people, again, as I said, it's public-private partnerships. So next is the adversary tiers 5 and 6 are intelligent adversaries, people that are actively targeting and creating their own vulnerabilities into the system. And that's where the higher grade research and work is actually going on between sort of DOE, DOD, DHS. What do we actually do about these systems? And again, like I said, 90% of the issues are down at adversary tier 1 and 2, but the more serious or higher consequence issues are coming from the adversary tiers 5 and 6. And that's where we start to talk about all the advanced machine learning techniques we can use to find things, optimizing your strategies for black start under cyber attack. more complicated asset inventory management, finding those unknown and hidden features that could be used against us. Here we also add the endure category. Once we've actually recovered, how do we keep going? How do we stop it from happening again? What are the components that are coming into play that can help us out in the future, so we have this keep going mentality? We're not just recovering and then going back to identifying again. We have to keep going, improving the system and moving forward. So when we talk about like what industry partnerships do and then what labs do on the next slide, the last adversary tiers are what the rest of us are actually working on as well. The NCIC this is the last slide I have here. NCIC is the National Cybersecurity Center, which has identified strategies you can use, which are the 7 recommendations for how people should work. These are not from us, they're from the DHS people. Basically on how you better manage a system and what the basic things you should be doing for an operational technology network. That's where we're talking about whitelisting applications, where you have a known application you use. We do this. We whitelist the type of software that we're going to use, which means our security people are monitoring the state of it and will tell us what the proper configuration and patch management is for it, avoiding us creating a vulnerability into our system, reducing your attack surface, basically identifying all the connections and monitoring them. Closing unused ports is an important one. We've done scans at a number of locations where we found things like 200 ports sitting open just because they didn't know what they had on their network. Having a defendable environment, managing authentication. That everyone's probably got into the whole multi-factor authentication thing recently. Secure remote access in your VPNs, and sort of monitoring and responding to what's going on, looking at the IP traffic, host-based monitoring and detection. So I finished up on this, on like what the 7 key strategies are. But yeah, there's further information is contained throughout this on links you can read and things you can learn about in there as well. So that's the last slide.
Thank you, Emma. We are taking questions for just a moment. I have one question for you, and I'm going to shamelessly promote some of our stuff right now, but we have something called a mini guide on how other agencies can work with PUCs during emergency management situations. I dropped that into the handouts folder. And then also our department has a whole branch, a whole team of 2 people, great, but 2 people who are dedicated to cybersecurity and critical infrastructure. So we have a bunch of resources now and that are coming out. But other than using and leveraging NAVIC resources, what can commissions do and what do to better understand what regulated utilities are doing to protect against cybersecurity threats?
It's kind of probably a big question. Reading all utilities, or especially the big regulated utilities, do have cybersecurity teams now. That's not an unknown. They've put together teams that are dealing with their OT networks and their IT networks, and are very much focused on dealing with the cyber issues. And a lot of them are working closely with the power side. One of the things, I mean, most of them are following the CISA work, the CISA, which I've linked to in here. Generally following what's going on there and reading the different alerts and bulletins that come in are a good way to learn what's happening and what's going on they come through fairly regularly now. The one that's probably more interesting is with the utilities that don't necessarily have those components. So a lot of the cyber people will also go and talk at conferences about what they're doing to protect their system. Again, a lot of it's sort of closed door discussions, but it's a challenge just now of how you take those lessons learned from the large regulated utilities and pass them down to smaller utilities that don't necessarily have the same resources. There's a kind of longer discussion on how to find out what they're doing. But there's also a lot of work going on through APPA and people like that to translate that information out as well. So a lot of the lessons learned from the large utilities are passing into these NCIC strategies also, things that they've learned to do based on events that have happened at larger utilities. So I'm not sure if that was entirely the greatest answer, but it's a challenge to work out what everyone is doing, I think.
Thank you. We appreciate that. Before we go to break, I just wanted to clarify that there are 7 key strategies listed on the screen right now. The number 5 is just listed twice, but there are 7 there. So.
Oh yeah, so sorry about that.